everyone. It's time for us to start section 2.4 on limits and continuity. So the big thing that we're going to do right away in this section is define what it means for a function to be continuous. We'll get there in a few moments. So I'll just say continuous means that there's no breaks in something, it's uninterrupted. So from a mathematical, a calculus perspective, what we're thinking about is a function with no breaks, no holes in the graph. So everything is nice and smooth. There's no holes here. To show something, so this is a continuous. To show something that is not continuous, I'm going to make a hole in it. So perhaps something, here's a different function. There's a hole, there's a jump here. This is not continuous. So when I go to the next piece of paper, we'll be giving a formal definition of what it means for a function to be continuous versus not continuous. I'll just kind of note here that a lot of physical phenomenon that we observe in everyday life are going to be continuous. So for example, temperature is going to be continuous. If we have something is warming up, the temperature is just going to be slowly increasing. It's going to, maybe it's 70 degrees, and 71, then 72, then 73, and so on and so forth. The opposite of this, imagine how silly it would be if at one moment it was 20 degrees outside and the next moment it's 80 degrees outside. It just jumps all the way from 20 to 80 degrees without going through intermediate temperatures. That just doesn't seem reasonable for that to happen. Or think about position, that as your car is driving along the road, it's moving continuously. You don't have a situation where your car is at one place at one moment, and then at the next moment it's 10 miles down the road. That just doesn't happen. So continuous functions are very nice, that we want lots of things to be continuous to be able to do calculus with them and model physical phenomenon. And so at this point, let's go ahead and have our definition. And so this is going to be a definition of continuity at a point. So we're going to assume that we have a function f which is defined on an open interval containing the value of x, some particular value x is equal, containing x is equal to c. Then f is continuous at x is equal to c if, here comes the definition, the limit as x goes to c of f of x is equal to f of c. And so we have a definition, we think about negating it. So if the limit does not exist, or if it exists and is not equal to f of c, then we say f of x is discontinuous at x is equal to c. So this is our definition. We'll do things with it in just a moment. But before we do those things, we'll just note that there's basically, if we want to say f is continuous at some value c, there's really three things that we're saying at the same time. So f is continuous, I sometimes abbreviate as continuous, CTS, continuous, at x is equal to c. There's three things that we're saying. So the first thing that we're saying is that f of c is defined. So we can't have a function that's continuous at a point at which is that point is just not part of its domain. That's impossible. So first thing that we're saying when f is continuous is that f of c is defined. The second thing is that we're saying that the limit as x goes to c of f of x exists. And so again, it might be possible for this limit to not exist. And then the third thing that we're saying is that these are equal. So in order for f to be continuous at x equals to c, we have to f of c to be defined. We have to have the limit as x goes to c of f of x to exist, and those two quantities have to equal. To extend the definition of continuity, we'll just say that if f is continuous at every point of its domain, we say f is continuous. So note that what we did before is that we were saying we define what does it mean for f to be continuous at some given point. So this piece of paper is only talking about what does it mean for f to be continuous at x is equal to 3 or something like that. This is saying that if everywhere in this domain, if it's continuous, we can just say the function is continuous. And we don't have to say it specifically for every single point. So to wrap up this video, let's just do an example to show that a given function is continuous. And let's think about g of x is equal to x to the 7. And we want to show that this is continuous. So how to show that this is continuous? Show continuous. So for every value of c, we have to do 3 things that we check. So the first is that we have to show that g of c, well, that's just equal to c to the 7th. This exists. So the function is defined everywhere for every real value of x. The second is that we want to check that the limit as x goes to c of x to the 7th, well, by properties that we were just looking at in the previous section, our basic limit laws. That's the limit as x goes to c of x, all of that raised to the 7th, which is going to be c to the 7th. So this exists. And finally, we observe that those two values are equal. So going back to our definition, f of c is defined, or in this case, g of c is defined everywhere. The limit as x goes to c of g of x exists everywhere, and those two values are equal. And so this shows that our function is continuous everywhere. So continuous on all of R.